Hi, in this session, I'll talk to you about comparing multiple groups. We'll discuss the motivation for doing so and the analytical techniques to implement such comparisons. In comparing multiple groups, we'll discuss the many techniques used for comparing multiple groups. These include various flavors of ANOVA. We'll also examine how to conduct ANOVA using a couple of examples. We're often interested in comparing many groups across some metric variable. For instance, a researcher may be interested in examining the market-related behaviors across a few segments, or a researcher who is about to test a few ads for the Super Bowl may be interested in comparing response to the ads based on consumer rating. Analysis of variance is a well-suited technique for handling problems of comparing multiple groups. The groups themselves, also known as fixed factors, may be either manipulated during the course of an experiment, or they may be pre-existing. We'll see what these are in just a bit. The groups as such are compared in terms of some metric variable, that is, an interval or ratio scale variable. One source of the groups to compare is manipulated factors. In the course of an experiment, one typically manipulates a factor of interest by creating multiple groups. One of these groups, of course, is a default called the control group. Other groups may be a treatment group and another treatment group, and so on. A company might have the ad that they're currently using, and then they may have 2 or 3 variations of it. The ad they currently have is a control group, and the variations treatment groups. There are many examples of such experiments. One of them is a widely cited study by Kramer and others, where they sought to see if emotions were transmitted over social media. To do so, they exposed a randomly selected group of Facebook members, news feeds that were altered or doctored to have mostly positive and neutral information. Another half of respondents had their Facebook newsfeed doctored to have mostly negative and neutral information in them. Over the course of about a month, they monitored the posts people made. Research results revealed that those who saw positive information in their newsfeed were more likely to say good things or positive things. Similarly, those who saw more negative information in their newsfeed were more likely to post negative information or depressing information. Bottom line, emotions were transmitted over social media. The test was conducted data was analyzed using ANOVA. So anytime you want to compare 2 or more groups, ANOVA is the way to go. The groups may also be pre-existing. For example, certain demographic categories cannot be manipulated. For instance, there's things that somebody has that are pre-existing, like gender or age group, or where somebody lives, or where somebody was born, their mode of payment, their country of origin. These are pre-existing groups. To compare these again, one could use ANOVA. One may maybe want to compare the amount people spend based on their the place where their home is located, or their country of origin, or their age category. If the number of groups is more than 2, then ANOVA is the only method available. So ANOVA can be used to model the effects of not just one factor, but even more than one factor. There are, of course, some requirements. Each factor can have 2 or more levels. The effect of a factor as such is called the main effect. When we examine the effect of many factors simultaneously or in combination, then this is called an interaction effect. There's an extension to ANOVA that accommodates covariates that is called ANCOVA, or Analysis of Variance. ANOVA can be expressed as a linear model with the metric variable serving as a dependent variable and the factors as independent variables. Based on the nature of factors and number of levels, there are a number of types of ANOVA. These include one-way ANOVA, two-way ANOVA, and so on, as generalized as n-way ANOVA, or ANCOVA. Let's look at an illustration of the various types with these two examples. In the dataset in front of you, as you can see, we have two columns, x1 and y. x1 is the factor we want to compare the levels of, based on another variable y. x1 has low and high. We want to know if the high and low groups differ across some metric variable called y. One could conduct an ANOVA. Of course, one could also draw this comparison by conducting an independent samples t-test. In fact, that is probably one of the more common ways of going about it. But just so you know, you could do the same thing using either t-test or a one-way ANOVA. Let's move on to a similar example with one difference. Now we have two columns x1 and y like we had before. The difference is x1 has not two groups, but three groups, low, medium, and high. So we want to compare the three groups of x1, low, medium, and high, in terms of some other variable y. In this scenario, the go-to technique is one-way ANOVA. This can be accomplished by conducting a number of t-tests, but that creates some associated problems. So the best way to approach this is a one-way ANOVA, possibly followed by post-hoc tests. We'll discuss that later, but one-way ANOVA is a go-to option in this case. I've been saying one-way ANOVA, and you're probably wondering, why is it one-way ANOVA? What is one way about it? Well, you'll see in the next slide. So here's an example where we have not just one factor, but two factors, x1 and now also x2. Now, this is a two-way ANOVA. It is a two-way ANOVA because we have not just one factor, but two factors, x1 and x2. Mathematically, you'll notice the equation has gotten to be a bit more complicated. Now, you see our equation that simply had x1 going into y now contains three elements in it. x1, the first factor, x2, the second factor, and its combination called x1 times x2. x1 is a factor with two or more levels, known as a main effect. x2 is a factor with two or more levels, and its effect is called, again, a main effect. The effect of x1 and x2 together on y is termed an interaction effect and represented as a cross product x1 times x2. Now, this can go on. We can go on adding more columns on here, which would serve as factors, and this would take us from a one-way ANOVA on a two-way, on three-way, and so on to n-way ANOVA. But just so we understand the intuition behind it, let's examine a three-way ANOVA. The difference, of course, here is now we have x1, x2, and x3. This model differs in many ways from the previous one. Not only do we have x1, x2, and 3 as our three fixed factors in the equation, but we also have cross products of every pair of factors, x1 times x2, x1 times x3, and x2 times x3. In addition, we also have a three-factor cross product, x1 times x2 times x3. Here, x1, x2, and x3 are each a factor with two or more levels. Their main effects are x1, x2, and x3. There are four interaction effects, three two-way interaction effects, and one three-way interaction effect. This is generally termed as an n-way ANOVA, but yes, more specifically here, three-way ANOVA. Now, let's take one column away. Now I've replaced x3 with c. The variable c differs from x3, or for that matter, x1 and x2, in that c is not a categorical variable or non-metric variable. Instead, c is a metric variable. C is a variable we suspect might have some sort of a role to play in some sort of an effect to play on y. It's called a covariate. The idea of including a covariate is to tease out any variance to increase the sensitivity of our tests. So here we have x1, x2, and c. Our equation has four terms, one for x1, x2, the product of x1, x2, and finally c, the covariate. Usually we're not interested so much in the effect of the covariate. We only include the covariate to remove any noise variance in our data, to lead to a more sensitive test, to really explicate the effects of x1, x2, or its interaction effect, x1 times x2. This is then a two-way ANCOVA. Here are some pictures to illustrate again all the techniques, all the different equations we have here. ANOVA is simple because there's only one fixed factor. Two-way ANOVA looks a bit more complicated with three terms: domain effects, one interaction effect. It's worth pointing out here that anytime you have two factors to consider, it is customary to examine their cross product called an interaction effect. It also makes the interpretation more nuanced and interesting at times. And with given below are the three-way interaction ANOVA effects, and lastly, the ANCOVA. Let's talk about t-tests versus ANOVA. If you only have two groups to compare, t-test is a great way to go about it. Specifically, I'm talking about here an independent samples t-test. Furthermore, if you only have one independent variable to examine, or one factor or two levels to examine, you can go and do a t-test. Now, an ANOVA can be used for many more applications than a t-test can be used for. While a t-test places a limitation on how many groups or how many levels a factor can have, a ANOVA does not have that limitation. With an ANOVA, the fixed factor may have more than two groups. Furthermore, an ANOVA can accommodate more than one factor simultaneously. It is an extension of the general linear model. Moving in, let's examine the mechanics of one-way ANOVA. Going back to our toy example, on the right we have x1 with three levels A, B, and C, and we're comparing the levels A, B, and C in terms of y. Mathematically, you can think about, or just based on data, you can think about us comparing the effects of A, B, and C based on some other variable y. So here's what it looks like. We're really interested in comparing this block to the next block and to the next block. To do this, what we're going to do is examine the variation within group and the variation between group. And if we notice that the variation between the groups is much more than variation within the groups, we'd be satisfied to conclude that the groups are significantly different. So let me go back and draw these boxes out one more time. When we look at the variation within a group, we're talking about the variation that exists within group A, that is across 6 and 4, and within B, which is 5 and 7, and the variation across between 6 and 4 within the group C. That is the within group variation. You'll see that in terms of just raw numbers, we're seeing a difference of 2 across each one of those levels of each group: 6 minus 4, 7 minus 5, and 6 minus 4 again. What we're looking for in a one-way ANOVA test is whether the differences across A, B, and C are far more than those within the group. If that is the case, our F statistic is going to be really huge, which in turn would lead to a significant statistic, which would lead us to believe A, B, and C are different. More specifically, at least one of the three is different. So there are some assumptions that ANOVA makes. One of them is that the categories of the independent variable are assumed to be fixed. The second is the error term is normally distributed. And lastly, the error terms are uncorrelated. Our first step in the process of conducting a one-way ANOVA is to compare all groups simultaneously, then compare pairs of groups. So it's a two-stage process. Our first step involves setting up hypotheses that looks as follows: YA equal to YB equal to YC. This is a null hypothesis. We're assuming the values of Y across all three groups are equal. If one rejects the null hypothesis, one would conclude that one of the three groups is different. We're going to conduct an overall test of quality group of means, which will then lead us to an F statistic for X1. If it is statistically significant, we'll go on to conduct pairwise post-hoc tests. Specifically, we'll contrast the average of, we'll contrast group A to group B in terms of Y, group B to group C in terms of Y, and finally group A to group C in terms of Y. These are post-hoc tests, thus require certain adjustment for type 1 error rate. Okay, here's some humor behind post-hoc tests. So the bottom line here is the reason behind, let me just read out the little story here, and we'll examine why this is humorous. So a researcher announces here jelly beans cause acne. Scientists investigate, and they've come back saying that they found no link between jelly beans and acne. And so that settles that. Somebody comes along and says, well, color might matter. So they go on testing a whole bunch of colors, and they examine purple jelly beans on acne and found that P is more than 0.05, and then onto a different color and different color. As you can see, we're examining a threshold of P, we're comparing P to a threshold of 0.05. With a threshold of 0.05 for alpha, one is admitting the chance of committing an error of 5%, or we're accepting a type 1 error rate of 5%. That is 1 out of 20 chances, 1 out of 20 times we'll make an incorrect kind of prediction with alpha 0.05. So here we go on through this process here. They cycle through, try out a whole bunch of colors from purple onto brown to pink and so on. And each one of the times the tests are non-significant. And they go on until they hit green, and they found out what green jelly beans are P is less than 0.05. And so they'll try a few more jelly beans, and they're all non-significant. So the news kind of highlights that green jelly beans are linked to acne. But bear in mind, they've conducted here, if you count through, 20 tests. Now, based on the type 1 error of 0.05, 1 out of 20 tests will be incorrectly predicted to be true. So in a sense, if you conduct your tests 20 times, one time you'll have a sort of a false positive. And that's probably what's being borne out here. And so the announcement, in a sense, is almost is a trivial announcement or trivial finding. For this reason, when we do post-hoc tests, we want to guard against this this sort of blunder here. So what we do typically in practice is, if our alpha is 0.05, when we're doing these a series of tests, what we'll do is we'll adjust this alpha to make it lower. So in practice, our alpha might only be 0.02 or something, depending on how many tests we're doing. This alpha might be much lower, and this adjustment is the kind of adjustment we can do is called a Bonferroni correction. Okay. Again, 0.02 is simply an example I'm giving you. The exact adjustment of the alpha lower depends on the specific Bonferroni adjustment applied, and that would depend on how many simultaneous tests have been conducted. Okay. Let's go on to actually looking at a data set and putting this whole knowledge to practice. So what we have here by way of data is a promotions experiment. The department store chain, the likes of Macy's, decided to experiment to see if promotion and coupon have an influence in sales. They wanted to make sure that they conducted a good experiment. So they randomly assigned their stores to one of 3 promotion conditions, high, medium, or low, and to one of 2 coupon conditions, yes or no. High promotion meant there was a big discount, medium promotion, a medium discount, and low promotion, a lesser discount. Half the stores had a coupon being offered, the other half did not have a coupon being offered. They gathered sales across these stores and they scaled them to a 1 to 10 scale to control for things like store-specific differences like square footage and so on. Finally, they gathered data on clientele. That is the loyalty of customers. This was computed based on an index of what percentage of customers hold a store loyalty card. So let's take a look at the data before we can go any further. Actually, let's go and let's take a look at the data before we can go any further. So here's our data. It's a data called promotion experiment and looks like this. So in our data, we have it's a small data set. We have 30 stores and 30 rows of data. And you'll notice for these 30 stores of data, 30 stores, we have a total of 15 stores that are in the coupon condition. Sorry, no coupon condition. Another 15 are in the coupon condition. Similarly, you'll find out here that we have a total of 10 stores in the promotion equal to 1 condition. 10 stores, yeah. And then 10 in the promotion 2 condition and so on. Just to see what these are, labels are, I'll click on value labels, you'll see what the labels are. So my bad, I misspoke a little while ago. We have, so 1 corresponds to coupon, 2 no coupon, 1 to high promotion, 2 to medium promotion, 3 to low promotion. So we have 10 stores in the, the first 15 stores in the coupon condition. The next 15 did not have a coupon offer in place. And then again, we had 10 of our stores that were in a high promotion condition, 10 in medium promotion, and 10 in low promotion. We have sales data scaled to 1 to 10 scale for all the 30 stores. We also have customer loyalty data. All right, so let me go ahead and now pull up a slide that I can annotate on. This will make it to a point where I can scribble notes on here that might help you. So the exercise we're going to work on is this one here. So our question is, does promotion influence sales? That's a big question here. We know our variable promotion has 3 levels. It's a factor and it has 3 levels. So our first step is going to be to compare all the groups of promotion simultaneously. Specifically, let me go and copy some stuff from a slide before. We're looking at this hypothesis, this pair hypothesis. So we copy paste that stuff over here. That's what we're doing basically. So right, so here we have it. We're going to look at why is the variable our outcome variable. In this case, is sales, because we want to compare sales, and we want to compare sales across 3 levels of promotion. 3 levels are high, medium, and low. So that's our hypothesis then. We want to see if the promotion varies across sales vary across different levels of promotion. And our H1 is that one of them is different. So note carefully here. While HO is saying that all 3 are equal, H1 is saying one of them is different. Because if you reject the null hypothesis, it doesn't mean all 3 are different. You could still reject the null hypothesis if any pair is different. And that's what H1 is reflecting. Having said this, let's go and run our analysis. So to run our analysis, these are the steps to follow. Let me go and apply these within SPSS. So we go to Analyze, General Linear Model, Univariate. Our next step is to move promotion to fixed factor. Sales is our outcome variable or dependent variable. Move it into dependent variable then. And we're going to do a few more things out here before we can go forward. One of them is we're going to check for, under options, for descriptive statistics, effect size estimates, and look at homogeneity tests. Finally, remember the warning I shared with you earlier about type 1 inflation of type 1 error rate? Well, we don't want our type 1 error rate getting out of control. So one way to control for that is to artificially dampen or reduce the size of our alpha level. We can do that by doing a Bonferroni correction. These are post-hoc tests. So I'll click on the post-hoc button and then move promotion over to the right. From the list below, I'll check the box for Bonferroni to indicate we want to adjust our alpha level using a Bonferroni correction. This will guard against inflation of type 1 error rate by making our alpha level more stringent or lower, basically lowering the bar. I'm sorry, raising the bar. Because when your alpha gets lower, it's making it more difficult for an effect to reach statistical significance. And that's it. Let's examine our output now. Our output says we have 10 stores in each particular condition. Furthermore, we can see here from the averages that in high promotion stores, sales were pretty high at 8.3. And in medium stores, they were 6.2. And in low promotion stores, they were 3.7. Just looking at these pictures, it seems to me like promotion is doing something here. Right? The sales are higher in stores with high promotion, lower in medium, even less in low promotion. There is an assumption that ANOVA makes of equality of error variances. Now, we're not going to worry about violations of this assumption, but just bear in mind that ideally speaking, you'd want to make sure that your Levine's test is non-significant. So what we're finding out here is that we look at Levine's test based on equality error variances, and our statistic out here for Levine's statistic is 1.353. That's an F test. And the corresponding p-value is 0.275, telling me that the variances of 3 groups, they might look a little different to you, but they're not significantly different. And that's a good thing because the test itself is testing for equality of error variances. So we're happy that the error variances are not different and they're about equal. Let's go to the heart of this test. The next table talks about the tests of between subjects effects. Here, we're examining the variable promotion. The variable promotion is what we are examining as our fixed factor impacting sales. We're interested in seeing if the 3 levels of promotion, high, medium, and low, have about the same sales or not. We can see here, we have a couple of numbers provided to us. One of them is a type 3 sum of squares. We have one for promotion, one for error, and one corrected total. We also have some numbers for degrees of freedom. The type 3 sum of squares are computed using the formula I showed you earlier. And the degrees of freedom are based on the number of levels that promotion has. Specifically, there are 3 types of promotion, so DF becomes 3 minus 1 or 2. The number of DF for error is simply the sample size minus number of levels of promotion. 30 minus 3 is 27. The ratio of 106 and 2 gives you 53. Similarly, 79.8 divided by 2.956 gives us a number of 79.8 divided by 27 gives us a number of 2.956. Lastly, the ratio of 53 and 2.9956 represent your between sum of squares and within sum of squares. That ratio is 17.944. In other words, this is telling us 53 is reflecting that there's much more between group variation than there is within any promotion group. And that number is reflected in a large F statistic of 17.944, which is less than 0.001. In other words, this leads us to conclude that that if you account for all these different numbers, let me put some of these numbers down here. 8.3, 6.2, and we had a third number here, which was 0.7. And we had the homogeneity test from Levine statistic of 1.35, corresponding p-value of more than 0.05. So, assume. So you can assume variances are equal at that point, and then we look at the sum of squares of x, error y that I highlighted before. But the key here is to arrive at an F statistic, which in our case turns out to be 17.944. The corresponding p-value for this statistic is well below 0.05, leading us to conclude that at least one of the three groups is different. We're comparing all groups simultaneously, and not all of them are equal. So we know one of the three groups is different. We don't know which one is different, or which ones are different. To investigate this further, we conduct what are called post-hoc tests. In our post-hoc test, we ask the question, which pairs are different? We conduct pairwise comparisons with a Bonferroni correction. That's what we are doing behind the post-hoc test button. Specifically, we'll contrast high promotion with medium promotion, high with low, medium with low. And I said contrast, but I'm talking about post-hoc contrast here now. Hence, we're using the Bonferroni correction. So let's hop over to SPSS and take a look at our next table. Under the post-hoc test table, you can see we have a couple of post-hoc tests noted. This table can be a little confusing because in a bid to make the table less repetitive, there's a bit of confusion. You can get confused about how it's laid out. So our first thing to do is to look at row 1, and we'll go along row and look at the contrast is high versus medium. We'll see high versus medium is 2.1 is a difference. If you look at the means of high and medium, you'll note the difference is in fact 2.1. Now, is this difference of 2.1 different from 0? That's the question being asked by the sig column or the p-value. Since that number is under 0.05, we're happy to conclude that high and medium promotion, stores with high and medium promotion have different sales. We can now move along and compare high and low. So next we compare high and low, and notice we have a merged sellout here. High corresponds to both the row for medium as well as for low. So I'll draw another box here for low. Maybe I'll use a different color. And here's our box for high and low. So next we compare high to low. And in that contrast, you can see that high and low have a bigger difference of 4.6, and that difference is also statistically significant. So we compared high, medium, and high and low. Let's move on to our last contrast, which is what's left, medium and low. As you look to row number 3, you'll notice here we've already covered row number 3, this one here. So instead, I'll go on to the one below, the one we have not done, which is medium versus low. So looking at medium versus low, we can tell now that medium versus low are also different. That is, medium is more than low because you can see the difference is positive 2.5. You can also derive this number from looking at the averages that we looked at before. What's most important out here is the p-value indicating that difference is statistically significant. In other words, there are three possible contrasts to look at: high versus medium, high versus low, and medium versus low. All three are statistically significant. Let's see what that means. So we can note out here, as we compared each one of these things one by one in order, each one of these had p-values that were less than 0.05. So let me just note the actual p-value and do it just this one time, and then next time I'll skip past that one. So the first one is high versus medium was 0.033. This was good. And that is awesome. The second one was just really, really small. So just say out here p less than. Third one, we had p equal to 0.09, and that was less than 0.05. Okay, here we go. So this is what we have. In conclusion, what can we see out here? Well, sales from high promotion greater than sales from medium promotion is greater than sales from low promotion. Or you can simplify this to say that, the more the promotion, more the sales. Or if you're trying to maximize sales, the recommendation to your boss would be to go with, to really ratchet up the level of promotion. Okay, let's blow past this and go on to looking at coupon influence on sales. So does coupon influence sales or not? Well, let's repeat the same process. Let's go back to our data set. Well, let's actually write down our hypothesis first. So our null hypothesis here is to use what we had before. I'll paste in the same hypothesis we had earlier, and let's see what this looks. So let's go and paste this hypothesis in. We had before. And again, I'll write these down as sales. We have looking at sales and y is sales over time. Now, notice we only have two groups here, A and B. With coupon and no coupon groups, there's no like group C present. So I'll just nix this completely. Normally, you would say each one is one of them is different, but with only two groups, you can go on and be more explicit and say, you could even have said sales coupon not equal to sales no coupon. For now, I'll leave it as one of them is different, but just understand it is equivalent to saying sales with coupon are not equal to sales with no coupon. They mean the same thing. And this is because we only have two groups. In the back of your head, you should also be thinking about the fact that it's odd we only have two groups here. Odd as in we're doing ANOVA with only two groups. We could just as easily use a t-test out here, independent samples t-test, to draw this comparison. Let's head over to SPSS right now and note how our data is set up. So as you can see, our data is set up as follows. We have here two groups, one with coupon and one without coupon. They are 15 apiece. And we're going to compare them based on a third variable, sales. Or second variable, excuse me. To do this, the method is pretty much the same as before. Analyze, general linear model, univariate. And now I like to always reset my menu here, reset that menu, and go and move sales over to dependent variable. Coupon is our fixed factor. And let's go as before to options and check a few boxes, one for descriptives, effect size, and homogeneity tests. Lastly, I'm clicking on Post-hoc, but I might get a little alert or something. I'm not. Okay. Now, I could set a post-hoc test out here, but let me tell you why it would be silly to do so. It would be silly because once ANOVA tells you, your test between subjects effects tells you that the groups are different, you already know that means coupon and no coupon are different. There is no third group. So at least one of them is different. The H1 is tantamount to saying coupon, no coupon are different terms of sales. So we don't really have to do a post-hoc test. If you do insist on doing post-hoc tests anyway, SPSS will tell you you don't need to, basically. So I'm not going to do this, but you can try it out on your own and see what it does if you're curious as to the consequence of it. I'm not doing it because it just doesn't make any sense to do so. Okay. Right. So with just this setup, I'm going to hit OK, and we'll take a look at our output that emerges from running this analysis. Here we have, we see that 15 stores had a coupon promotion, 15 didn't. And sales were in these stores were as follows. We had 7.4 and 4.73 units of sales. That looks, just looks material and meaningful. The standard deviations as such, if you compare them out using a Levine's test, you find out that that test is, again, non-significant, which you're happy about because that means that the assumption of equality variance is being honored. Moving along, let's get to the most important part of our test, which is to examine whether, in fact, coupon has an effect on sales. So you look at the row for coupon, and if you just focus on just that row for coupon, that really has the result we're looking for. Basically has the type 3 sum of squares, which doing some, again, arithmetic out here, we get to an F statistic of 11.268. That corresponds to p-value 0.002, and that's that. What does that mean? It means our F statistic is pretty big, 11.268. And the corresponding p-value is 0.05. Therefore, sales are higher. Sales with a coupon are different from sales without a coupon. That's it. Very, very simple conclusion arises from this thing, from looking at, again, coupons. Okay. Now, here's a visual, as I had a visual for the promotion also. These boxes kind of illustrate to you what is being tested by Levine's test. Essentially, Levine's test is looking to see, just symbolically speaking, if these boxes are equal or not. I say symbolic because it's really comparing variances, not this interquartile range being represented here. Okay. So let's move along here to what is an n-way ANOVA. Probably wondering, okay, we're already jumping one way to n-way ANOVA. Well, n-way is generalized generalization of two-way, three-way, four-way ANOVA, and so on. And the point here with n-way ANOVA is, what if you want to examine the role of another thing, second thing, third thing, and so on in practice? A marketer, for instance, may be interested in examining the effects of not just changing one thing, but 2, 3, 4, 5 things. They might have changed the ad campaign, they might have changed the packaging, they might have changed the price, and they might want to look at the joint effect of all these changes on, let's say, sales. So let's move along and take a look at how you would conduct this sort of test. In our example, so in terms of the mechanics of it, because we're examining the effects of two factors, the picture looks on the toy example looks a little different. We now have an x1, one fixed factor, x2 a second fixed factor, and we've got a in y we've got a dependent variable or outcome variable. We're looking to see if the effect of x1 on y is significant or not, x2 on y is significant or not. These two are called main effects. But before we can examine the main effect, what we need to examine is the effect of x1 times x2. Specifically, examining the effect of the the joint effect of x1 and x2. In other words, do x1 and x2 interact in influencing y? By default, we're going to assume here that no, they don't. HO is x1 and x2 do not interact in influencing y. That is whether you look at them individually or separately, it's no different. H1 is saying x1 and x2 interact in influencing y. It basically means that you put the variables, to put the factors together, and they act differently than if examined individually. You might know of a number of analogies of this experience in life, where you find certain teams of people on when they when they get on a task, they are the sum of the individual contributions is far greater than the whole is greater than the sum of the individual contributions. And then you've got groups where you throw a bunch of people in together and they're worse off than if they were their own. In both these cases, you have an interaction effect. In one case is positive, in one case is negative. If, however, you found no difference in the contributions of people while they're working together or separately, well, then you've got a zero interaction scenario. That's what HO is examining. So our first step is to examine the interaction effect. And once we're satisfied that is not present, we'll go on to examine a main effect of each factor. And then lastly, we'll examine our main effects of each factor after the interaction effect. And then we'll go on to examine post-hoc tests for each factor individually. So 3 steps out here. So I'm going to blow past the math involved out here and go right to our little problem. Our interest here is to examine the effect of promotion and coupon influencing sales. Let me go and copy paste this snippet into the slide. So I will modify it in a second. So here is the interaction effect being examined. So our research question here is, do promotion and coupon influence sales? So HO is examining whether X1 and X2 interact in influencing sales. So X1 in our case is promotion. And X2 is coupon. And Y is sales. Saying they don't interact to begin with. That is, it doesn't matter whether the two marketing activities happen together or separately, it doesn't matter. So we're going to examine this hypothesis, and we'll examine a plot along the way as well here, and then we'll examine main effects like we did before, and then on to post-hoc tests. Okay. Some of this will be repetitive as we go through, you'll notice very soon. Now, to run this thing in SPSS, here's what you'll be doing. Let me go on to actually put this to practice. Analyze, general linear model, univariate. We're off to the races here, but let me reset again. Our dependent variable sales. The first thing we ran here was with just promotion. This time we'll include promotion and coupon. This is a two-way ANOVA. I'll check a few boxes for descriptives, effect size, and homogeneity tests. And lastly, ask for post-hoc tests, but only for the 3-group factor. So as a thumb rule, you only need to conduct post-hoc tests if you got more than 2 levels in a factor. Lastly, here's something new. We'll build a plot out. Our plot will kind of graphically represent the interaction effect. And that, I think, is a handy way to understand what kind of effect we have. So I'll move promotion over to horizontal axis, coupon over separate lines. In theory, it doesn't matter what goes on horizontal axis, what goes on separate lines. But I just feel the visual is a lot more pleasing if the factor with more levels goes in the horizontal axis, the one with fewer levels goes on separate lines. Coupon has 2 levels, hence in separate lines. I'm not going to hit add, this is an important part, to put it down in their plots. And that's it. Continue. and hit the OK button. Let me head over now to the output window to see what SPSS did for us. Okay. Now, if you look at these numbers, we can learn that for each promotion, we have 10 stores. Each coupon, we have 15 stores, each coupon type, that is. We also have a table that is a bit more complicated than the last one, because now we're looking at not just promotion and coupon individually, but we're looking at them as a combination. So we've got to look at what happens when promotion is high and the coupon is being offered. Or what happens when promotion is being offered but there's no coupon. What about medium promotion and a coupon, medium promotion, no coupon? There are all these different combinations to look at. So you're looking at 6 combinations then of promotion type and coupon type. Let me switch over to a slide where I've plotted this out to explain the concept of an interaction, why this is important, why we care about it. Okay. So to understand interaction, let's just first begin by making a very simple bar chart out here. This is made with a different software. SPSS doesn't make this one, but it's good for, it's easier to kind of visualize, so I made it using that software. You'll notice here, the bars show you how much sales each promotion type yielded. Low was 3.7, medium was 6.2, high was 8.3. These are the numbers we got from running the first ANOVA we ran. So we know the recommendation to management is if you want to boost sales, all else being equal, increase your promotions from low to medium to high, period. The question now is, what if there's a coupon also in play? Would this recommendation change? Let's look at a picture. So here's a picture with coupon, without coupon. Let's look on the left first. What can we learn from this? Well, if a coupon is not in place, not being offered, if you're only doing promotions but no coupon, you go from low to medium promotion, your bump or boost in sales is 2.8 units. Down 2.8. As you go from medium to high, you get a boost of 7.4 minus 4.8, which is 2.6 units. Now, that's interesting. So it seems like the more the promotion, the more the sales. But we already knew this. Let's see what happens if a coupon were in play. If a coupon were being offered, our sales boost would be from 5.4 to 7.6, a boost of 2.2. In other words, if you look back, when we didn't have a coupon, we got a boost of 2.8 units in going from low to medium. Now it's only 2.2. The jump in sales from offering a medium over low promotion is less now than it was for no promotion condition, no coupon condition. Let's examine what happens in this scenario here. As you go from medium to high, your bump is only 1.6 units. So you're noticing, hopefully, that the impact that promotion is having on sales is less when there's a coupon in play than when there wasn't a coupon in play. This is suggestive of an interaction effect. Okay. We have directional interaction at this stage. What we don't know is if this is statistically significant. In other words, would this be reproducible in a different sample? We don't know yet. Let's take a look at a different graph now from SPSS before we can draw any inferences about the interaction effect. So I'm going to skip past the output that follows and go straight to the plot. We'll come back to the output later. Okay. So here is our profile plot. What we have here is, I think, a pretty interesting graph. So we have here high, medium, and low promotions on the x-axis. And the y-axis, you've got your sales. You've seen this picture before with a bar chart. Now, the same thing the bar chart was bearing out is being borne out by the line graphs here as well. What you want to focus here, what you want to focus on here is the fact that as you go from, low to high promotion, in the coupon condition, there's a boost. There's a bigger boost in the no coupon condition. This bump is higher in the no coupon condition than the coupon condition. Right? So what we have, our takeaway then is that there is directional interaction. You can also think about this as in terms of the lines themselves. The lines are intersecting, albeit off the graph paper. So if you were to extrapolate these lines out into the future, further out, the blue line or the green line, they would at some point in time, cut or intersect there for this suggestion here of there being some level of interaction at some point in time. Okay. All right, now let's go back and see if this actually is significant or not. So as before, going back up to our table earlier, and then our Levine's test, we'll take a look at that, attribute to Levine's test really quickly here. It is as before, as has been the case in our previous examples, is non-significant. We're satisfied. So going forward here, on to test it between subjects effects. This is important. This is good, or this is well, it's important. So we see how here is we'll begin by looking at the interaction effect. Now, the effect of promotion coupon simultaneously on sales. So there's no row that says it's the interaction effect. So we're going to look around. If you recall, interaction is represented as a cross product of the two fixed factors. So look through on the leftmost column, and you'll notice here under source, there is a row for promotion star coupon. This is what represents the interaction effect. So our interaction effect is, we'll go along the right to our F value 1.69, P value 0.206. In other words, our interaction effect is not significant. Yes, it was a huge lead up, a huge build up to a big expectation that there would be an interaction effect. I pointed out all the ways that the interaction is directional. Indeed, it is directional, but it is not strong enough to reach the level of statistical significance. In other words, no interaction. Once you have concluded that there is no interaction, now you can proceed to examine the main effects. The main effect itself is telling us the following. We look at promotion. Here you can see promotion is a main effect. And then we can look at a coupon. That is a main effect also. So our takeaway here. The interaction effect is non-significant. We look at the main effects one after the other. We notice the main effects of promotion and coupon each are statistically significant. In terms of which one of these two effects is stronger, we know that promotion times coupon is not significant, so we can just ignore that row altogether. Interaction effect. We can focus here on the variables that are statistically significant, which in this case are promotion and coupon. Of the two variables, in a statistical sense, you can compare the effect size, the effect the promotion coupon have on sales, by looking at the partial eta squared. Partial eta squared tells us that promotion with a partial eta squared of 0.821 has a stronger effect on sales than does coupon, which has a partial eta squared of only 0.697. Now, having done this, we can go on and interpret the rest of the output. So we've examined the interaction effect, section part 1. Then we examined the main effects, part 2A and 2B. And part 3 is to conduct post-hoc tests like we've done before. That is a repetition of what we've done before, so I'm not going to go over that again. Okay, so our takeaway from this whole process would then be to go back to our slide and put this all together. Right, so we went through this test out here, comparing, looking at the interaction effect, concluded the F statistic was kind of small, P was about 0.206. So 1.69 and 69 this was 0.246. And that led us to basically say that this is, interaction is not significant. We examine the main effects, arrive at the same conclusions before. And lastly, we would then go on and look at the pairwise comparisons for only promotion, not for coupon, because again, coupon only has 2 levels. So this is then how you would conduct a 2-way ANOVA. Let's move along and examine another scenario, one of an ANCOVA. What in the world is ANCOVA? ANCOVA is analysis of covariance. Now, there are times when you conduct an experiment, you check all the boxes, do everything correctly, but you're just not sure that some other extraneous variable is not throwing a monkey wrench into your experiment. There are other times when you do not have the ability to experimentally control for differences across groups because they're pre-existing groups like based on demographic variables. In those cases, even more important to consider the potential contaminating effect of some uncontrollable variable. You can explicitly control for these or statistically control for the effect of these variables by including them in the ANOVA as a covariate. Because we'll be using them as a covariate, it's called ANCOVA, analysis of covariance, not just analysis of variance. In terms of the approach of it, it's very similar to, or rather how to do it is very similar to the way we went about doing a ANOVA. So we were examining here whether promotion and coupon influence sales after controlling for clientele. In our problem, clientele is what we are going to examine as our potential contaminant variable. So the point here is that we know we have found promotion, coupon individually affect sales. But, is it possible that maybe these effects are driven, or the effect on sales driven by something else like customer loyalty? Granted, we conducted a good experiment. We randomly assigned stores to different conditions, and therefore you'd expect the stores would be, there'd be no other extraneous variables. But another person would argue you only have 30 stores, so you could have controlled for everything. So what about customer loyalty that might vary across stores? There's a vast amount of research that indicates loyal customers respond to promotions differently from transitory customers or transactional customers. So we are going to now explicitly account for the effect of customer loyalty or clientele by including that in the model as a covariate. This would then be called an ANCOVA. So our setup is the same as before. We're examining a 2-way ANOVA with interaction effect and also accounting for clientele. To do this, we'll go into GLM, univariate, and the setup is identical to the last one. So in this case, I'll get a little lazy instead of setting it up again. All I'm going to do is move clientele over to covariate. Everything else is the same. That's it. Okay. If you go to output now, you'll see in the output window, we have here, as before, a set of descriptives for number of observations, averages, and then we have our Levene's test showing up, non-significant, thankfully, and we go on to our test of between subjects effects. Let's begin by seeing how is this different from the previous analysis. If you look carefully enough, you'll notice the new row added on is clientele, or our measure of customer loyalty. So you can see customer loyalty measure, or clientele, has a p-value of 0.363. We thought customer loyalty might have a bearing on sales, and so we thought we'll statistically control for that. Turns out it doesn't. So no issue. If it did, that would have been fine also. Basically, including a covariate gives a more pure measure of our fixed factors. In other words, the conclusions you would draw from an ANCOVA are more reliable than those from just an ANOVA without a covariate. We can verify now our results from before are the same, or perhaps better. Our interaction effect still remains non-significant, and our main effects remain significant. As far as that goes, our conclusions are identical to what it was before. Okay. So we've gone over now a whole, we've gone over two one-way ANOVAs and ANOVA, two-way ANOVA with a interaction effect and an ANCOVA. This basically wraps up the different kinds of comparisons you could do across groups. The one thing that is noteworthy about what we've gone over so far is that every comparison we made was across, if you think about a spreadsheet, across groups of rows. What if you're comparing across groups of columns? Well, then you would do a repeated measures analysis. This is the multi-variable analog to a within, a within subject t-test, right? So we did t-tests earlier, and if you're doing a t-test for comparing columns, a paired samples t-test, you want to extend the paired samples t-test to more than 2 columns of variables, you would do repeated measures ANOVA, or repeated measures analysis, more simply. So it's beyond the scope of this class, so I'm going to go on, not expose you to that. You can find that quite conveniently in the SPSS menus. And under certain circumstances, when your metric variable is, when your dependent variable is not metric, then you've got to turn to some non-metric methods for ANOVA, and those are kind of described out here. Another variation of ANOVA is MANOVA, or multivariate ANOVA. This is where you are looking to examine the effects of the factors on many dependent variables. So imagine a variant of variables, so like 3-4 dependent variables. That's MANOVA, or multivariate analysis of variance. Again, beyond the scope of this class, so I will not delve into that. Okay, let's review some of what we've done right now with some examples, with another example rather. In this example, we're going to work with the wages data. So this data set here on wages that I'm going to show you in a second includes information on, I haven't described it here. It includes some information on people's demographics and how much money they earn. Let me pull up the data set and take you there. So here's our wages data set. The wages data set includes information on people's earning, their height, gender, race, education, age, and height category. Here, in our data set, that is, earnings in dollars, height in inches, gender is male, female, race, there are 4 races here, white, Hispanic, African American, Asian. Education is based on years of education, age in years. Height category is based on how tall somebody is. It's been kind of broken up into 3 bins, short, average, tall. Our first order of business here in this analysis is to examine if race influences earning or not. Let's begin with that. We sure hope it doesn't, right? So let's take a look at our variable race and earning. Now, race is a fixed factor. It has 4 levels. Verify that. So race has 4 levels, take my word for it, I guess. I will actually run a quick descriptors here so you can be convinced about it. So race here is the race variable. So race has 4 ethnicities or races involved out here. And here's a breakdown of them by percentages. Our goal here is to assess whether race, earning differs across races. So we'll analyze general linear model univariate, and we're going to bump race as a fixed factor and earning as a dependent variable. Set up our options, and we'll request post-hoc test because race does indeed have more than 2 levels. Having done all that, let's interpret the output. From looking at the averages, we can tell that it does seem like there are differences across different races. We see African Americans making less than Asians, Hispanics making less than everybody, and whites making the most amount of money. Actually, yeah, whites making the most amount of money. Our Levine's test here was significant. We would hope it wasn't significant, but for this class, we're going to ignore that that result that's not so desirable. Let's go on to our test between subjects effects. Here we can see the effect of race. So race has basically an F statistic of 2.324 and a p-value of 0.073. I'm relieved. At least our data says that race does not matter. In other words, what we found out here from this analysis is that when we looked at a null hypothesis that the earning of African Americans equal to earnings of Hispanic, equal to earning of Asian, equal to earning of whites, we don't have enough evidence to reject that null hypothesis because the p-value is 0.073. So there's really no need to scroll down anymore. I can stop here because we've concluded here the 4 races have approximately the same amount of earning. That is, the differences aren't statistically significant, so no need to compare pairs of races anymore. Stop right here. All right, let's consider another example. The same data set. We can examine the effect of gender next on earning. So for this one, analyze general linear model, univariate, bump race out and remove gender in here. Now, because we have the variable gender, in general, in our data is only 2 levels, there is no need for a post-hoc test. We'll run this and see what we find out. Here's what we get. In terms of, you see a startlingly big number, just in the face of it is a big number, for income for males and females. Again, our Levine's test doesn't really meet the assumption. We're not going to worry about that in this class. Let's move along. And we'll lastly look at, most importantly, by now you probably your eyes have already darted over to the row to identify here. For gender, you can see our p-value is a whopping less than 0.001, telling us that gender does have a significant effect. Gender effects in earning or income. More specifically, the earning of males and females is equal is an incorrect hypothesis. We reject the hypothesis that earning of males equal to earning of females. So we conclude the earnings of males and females are different, unfortunately, at least in our data. Let's go on now to another problem. We're now going to examine the effect of height. How would height matter? Let's take a look. You would think height shouldn't matter. We're going to use the variable height category here. It's a fixed factor to examine the effect on earning. Now, what you don't want to do is use height category as your fixed factor. If you do that, SPSS will get stuck because you gave it an unsurmountable problem. So we set it up by analyze general linear model, univariate, and we'll bump gender out of here, and we'll move in height category. This is the fixed factor version of height, where height has been binned into short, average, and tall. Because we have 3 categories of height, I'm going to ask for post-hoc test for height category. Verify the options are checked. We can now hit OK. Just before I hit OK, just bear in mind our HO here is income of short people equal to income of average height people equal to income of tall people. So our again, our descriptives here indicate some differences in earning. And again, we're going to ignore the fact that this test is significant. It should have ideally been non-significant. Okay, on to our key output here. The effect of height category. Does it matter? Does height matter? Yes, it does. Our F statistic is 56.54, p-value 0.001 or less than 0.001, indicating to us that height does matter. In other words, the assumption that earning of those who are short equal to earning of average height equal to earning of tall people are all equal is rejected. Which leads us to the question, okay, so who's making the money? We're now going to compare all pairs of, people, all pairs of height, in a sense, height categories. So here we examine the results one by one, short versus average height. There's a difference. Short versus tall, the difference is significant. Lastly, average versus tall, there's a difference. So all 3 of these are statistically, all 3 of these differences are statistically significant. In other words, short people make less money than average height people, make less money than tall people. Okay. Let's go on to one last analysis now. We are now going to take things together. So you know from the previous analysis that we have concluded that females get the short end of the stick, making less money than males. Short people get the short end of the stick, pun not intended, making less money than those of medium height or average height or tall. Let's examine the joint effect of sort of height and gender. Okay, so we're going to look at here, just express the hypothesis. We're looking to see if height and gender do not interact, whether they have an interaction effect or not. Each one that they don't interact, each one there is interact. In other words, we're kind of wondering, is the effect of height on earning, is it dependent on, is it male or female, or does not matter? It's possible we find out that there's a height premium in terms of salary that applies for one gender, but not for another gender. This would be indicative of an interaction effect. That's what we're looking for. So heading over to SPSS, we'll run this one last test out here. So I'm going to analyze general linear model univariate. And I'm going to move in gender as well to our fixed factors list. Under post-hoc, there's no need to move gender to the right because there are only 2 levels to gender in our data set. Under plots, I'm going to move height category over to horizontal axis, gender to separate lines. Click add. Now I think we have it all set up. Hit OK. Last thing we'll do is we'll go to the output window and take a look at our results. So what we have here is for short people, you kind of see males are making more money. Okay. For average height people, again, males are making more money. For tall people, again, males are making more money. Okay, that is not telling us much. So just looking at that, it seems like males are making more money regardless of height. So that's telling me maybe there's no interaction at all here. If you look more closely, you kind of see here, the differences here are, are not the same across the three comparisons. We'll get more color on this from a graph. So let's look at the graph, our profile plot here. So here we are. Now, this should be interesting, hopefully for you. Look carefully at this graph. For the blue line here, that's a female line. As you compare women who are short, women who are average height, women who are tall, there's clearly an increase in salary. But that increase is not huge. And obviously, I'm using this in a relative sense. Look at the green line, the line for males. For males, as you go from short to average to tall, there's a huge increase in earning. In other words, it seems like there's men have more to gain from being tall than do women, as far as salary is concerned. So far, it's smoke, no fire yet. I built it up last time. We found out the interaction was not significant. Let's check if this interaction is in fact significant. Okay. We have our data here. We'll begin by highlighting or looking at the interaction effect. And yet again, I built it up. I made it seem like there's a big difference, but in fact, there isn't one. You compare height category, gender, look at the interaction effect, and that p-value is not significant. In other words, what seemed to me like an interaction effect really was not statistically significant. So we're down to looking at our main effects again, and we conclude then that the effect of height on earning is not contingent upon somebody being male or female. The last thing I'm going to do here is I'll bring up to you a curious little data set shared by Andy Field. It's really good data set because it kind of highlights in a humorous way the interaction effect. So let's take a look at this. Okay, so here's a data set I'm going to share with you right now. It's a data set that Andy Field, author of Discovering Statistics in SPSS, has shared, and it has information about some kind of, it's a head turner in terms of the subject here. It's about something called the beer goggles effect, and specifically what it means is that the more alcohol somebody consumes, the more attractive other people, the opposite gender, appears to be for heterosexual people. So he conducted this, he describes in his book, he conducted this experiment where he invited a bunch of people to come to interaction, a place, and some people were offered no alcohol, some people were offered 2 pints of no beer, some were offered 2 pints of beer, some were offered 4 pints of beer. So you had random assignment in terms of alcohol level. And then some who came were males, some who came were females, and they were allowed to mingle with whoever they wanted to. And somebody else was somebody, a research assistant was examining who the subject was talking to at the end of the evening. Specifically, rating the attractiveness of the person the person was talking to. Let's say, you got this person, Stacy. Stacy comes to the party and she gets, beer. She gets water instead of beer. She gets a cup with 4 pints of 4 pints of water. And some research assistant will rate the attractiveness of the person she's speaking to, the male she's speaking to at the end of the evening. Okay? And that's the attractiveness of them. So the beer goggles effect is that basically that the more somebody drinks, the more easy, lower their standards are. They'll talk to pretty much anybody, regardless of their physical attractiveness. Okay, so let's take a quick look at the beer goggles effect. Specifically, the idea is the more alcohol somebody drinks, the less attractive their date would be, right? Because they're willing to speak to somebody without concern about their appearance. That's the idea of the beer goggles effect. So we'll set us up. And okay. So the findings of the analysis are as follows, is that you look at the attractiveness person they're talking to and you find out, well, from no pints to 2 pints, it doesn't really matter, not much difference in the attractiveness, but at 4 pints, a huge drop in attractiveness of the person they're talking to. So I guess at some point the beer hits a spot, and then people are less discriminating in terms of the physical attractiveness of the person they're talking to. So we go down this list and we see in terms of the p-value, in fact, it is indeed the case. So alcohol has a significant effect on attractiveness of date. We look at pairwise contrast here, post-hoc contrast or effects, and we kind of notice here that there's a difference here that is kind of nuanced, that between no beer and 2 pints, there's no difference. Or you look at no beer and so two pints or 4 pints, there's a difference. Similarly, no pints, no beer, and 4 pints is a difference. So 4 pints seems like a tipping point where people, attractiveness of date is much lower when somebody has 4 pints of beer. So this is basically what the beer goggles effect is supposed to be. So let's take a look at what happens when you were to account for another kind of variable here. So in this study, we had male and female participants. So what if you examined, gender as a factor? In other words, the argument here is that we're studying the beer goggles effect, but does this vary based on the gender of the subject? In other words, if one group is somehow affected by the beer, is another group equally affected? If they are, there's no interaction. If they're not, there's an interaction effect. Let's take a look at our results. So we're going to move gender into the fixed factors column. And I got a plot out here. And set this up. Okay. So on to our output, and we can see out here that as you look at the data here, there's some numbers here that paint a picture about the effect of beer and across genders. If you eyeball those numbers, you might see something kind of striking going on here. Let's visualize this to get a better sense of the effect. Now, just from looking at this graph, you should notice that one thing is obvious: the lines are intersecting. Intersecting lines usually imply a pretty strong interaction effect. But let's understand this effect to get to the nuance of the interaction effect and why it's important, why we care about it. The data is telling us that if you follow the green line, when females have, sorry, let's follow the blue line. When males have no beer, the attractiveness of data is pretty, they're talking to attractive people. At 2 pints of beer, they're talking to about as attractive people. But when they have 4 pints of beer, they're just going off a cliff, right? At 4 pints of beer, they're talking to pretty much anybody, right? The attractiveness of data is much lower at 4 pints of beer than at none or 2 pints. That's the beer goggles effect. We already know that. But what about females? When they have no beers, they go to 2 pints of beer, there's an actually increase in the attractiveness of their date. Interesting enough. At 4 pints of beer, there's a drop, but not much of a drop. Look at males, look at females. For males, there's a huge drop. Females, not so much. Hopefully this example was enlightening enough for you to truly understand the kind of what an interaction effect means. Okay, so what we've done here so far is we have in this session examined find my slide. Okay, so we examined here the purpose, motivation, methodology, and mechanics of ANOVA. We performed a number of exercises, and we also examined some advanced topics and looked at a couple of illustrations of the various kinds of ANOVA. Hope this was helpful. Thank you.